One routine switch did not create the Apollo 13 crisis by itself. The danger was already sealed inside oxygen tank number 2. Damaged hardware, incompatible voltage assumptions, overheated wiring, and warnings that never became a launch stop. When the crew later stirred the tank, a normal command met an abnormal machine. 3 astronauts were then roughly 200,000 miles from Earth with electricity, oxygen, and water beginning to disappear. Apollo ground equipment was changed to supply 65 volts, while the oxygen tank heater system had originally been designed around 28 volts. The heater itself could tolerate the higher supply, but its thermostatic switches were not properly upgraded. That mismatch mattered only if the heater remained powered long enough for the switches to open. It was a latent design trap, invisible during ordinary operation, destructive under an unusual test condition. The oxygen tank later assigned to Apollo 13 had previously been installed in another service module and removed for modification. During removal it was jarred, and a fill line assembly was damaged. The tank was repaired, tested, and eventually installed in Apollo 13. None of this alone proves the later explosion, but the history explains why the tank behaved differently when technicians tried to empty it before launch. During the countdown demonstration test, oxygen tank number 2 would not detank normally. Engineers tried pressure through the vent line, but the quantity remained high. They chose to boil the oxygen away using the tank's internal heaters. The method worked, yet it kept 65-volt ground power on the heater circuit for about 8 hours, far beyond normal spacecraft use, and created the condition the mismatched thermostat switches could not safely control. NASA later investigation concluded that the thermostatic switches likely welded closed. Temperatures near the heater assembly may have climbed to roughly 1,000 degrees Fahrenheit, severely degrading Teflon insulation on wiring inside the oxygen tank. External instruments did not reveal the internal damage clearly. The tank could still be filled and appear serviceable, leaving exposed conductors immersed in high-pressure oxygen for the flight. Jim Lovell, Jack Swigert, and Fred Hayes lifted off toward the Moon. An early center engine shutdown in the Saturn V's second stage was compensated for by longer burns from the remaining engines and the third stage. The spacecraft reached the intended trajectory. For almost 2 days, oxygen tank number 2 appeared to perform normally. The mission objective remained a landing in the Fra Mauro region. During a routine fan cycle, the quantity indication for oxygen tank number 2 moved off scale. The crew and controllers treated it as an instrumentation issue because pressure and temperature did not yet announce a catastrophic failure. Stirring cryogenic tanks was normal. Fans mixed stratified fluid so sensors could give useful readings. The procedure that would expose the damaged wiring was therefore not reckless improvisation. It was an ordinary checklist action. Capcom Jack Lausma asked the crew to stir the cryogenic tanks and supplied pointing information for observing Comet Bennett. Swigert acknowledged the request. The spacecraft was coasting quietly after a television broadcast. Nothing in the words sounded urgent. That contrast is central to the accident. The command was mundane, while the electrical environment inside tank number 2 was no longer safe. The oxygen tank fans were switched on. Telemetry immediately showed pressure changes and electrical disturbances. Investigators later reconstructed a likely short circuit in damaged wiring, igniting insulation in the oxygen-rich tank. The precise internal sequence could not be watched directly, but the synchronized voltage, current, pressure and later structural evidence placed the initiating failure in oxygen tank number 2. After telemetry recovered, the quantity reading for oxygen tank number 2 went off-scale high, then became erratic. A failed indication did not mean extra oxygen, it meant the measuring system was being destroyed. Temperatures, flow rates and bus voltages began telling different parts of the same story. Mission control had only fragments, and the crew had warning lights without a complete diagnosis. Swigert reported that the crew had experienced a problem. Lovell clarified that the main B electrical bus showed under voltage. Hayes described a large bang. The famous exchange was not a polished declaration, it was the opening of a diagnosis. At that moment, neither spacecraft nor ground team knew that an oxygen tank had ruptured and that 2 fuel cells were about to become unavailable. Main bus B voltage collapsed and fuel cell 3 failed. Seconds later, bus A also sagged. Apollo's fuel cells combined oxygen and hydrogen to produce electrical power and water, so losing oxygen threatened 3 essential resources at once. The crew tried normal electrical recovery actions, but this was not a breaker that could simply be reset. The reactant supply itself was escaping. Lovell looked outside and reported gas venting into space. That observation changed the diagnosis. Oxygen tank number 1 was also losing pressure, probably because the explosion damaged a line or valve. With the remaining oxygen heading toward zero, the last fuel cell would die. The command module could no longer support the crew for the trip home. About an hour and a half after the bang, controllers and crew were thinking explicitly about using the lunar module Aquarius as a lifeboat. It had been designed to support 2 people on the lunar surface, not 3 people for several days in deep space. Powering it up quickly while preserving the command module's batteries demanded new procedures, rapid calculations and strict control of every consumable. Controllers chose a trajectory that carried Apollo 13 around the Moon and back toward Earth. The lunar module's descent engine provided correction capability, but burns had to be planned for a spacecraft stack never intended to be flown this way. Navigation, attitude, and power were interconnected. A wrong burn could miss the recovery corridor. Too much electrical use could leave the crew unable to complete re-entry. 3 people were exhaling into a cabin designed for 2. The lunar module's round filters could not consume enough carbon dioxide for the full return, while spare command module filters were square. Ground teams improvised an adapter from materials available on board: plastic bags, cardboard, a hose, and tape, and transmitted the procedure. The celebrated solution addressed geometry, not magic. It forced cabin air through the usable lithium hydroxide canisters. The crew reduced power and water use to severe levels. Cabin temperatures fell and condensation formed. Haze became ill. Mission Control built and tested an unprecedented command module power-up sequence so the batteries reserved for re-entry would last. Every amp and minute mattered. The rescue depended not on one heroic fix, but on dozens of compatible procedures arriving in the correct order. The crew jettisoned the service module and photographed a large exterior panel missing beside the oxygen tanks and fuel cells. Until then, no one had seen the full structural damage. They later released the lunar module and powered the command module for re-entry. The improvised lifeboat had completed a job it was never designed to perform. The command module splashed down safely near recovery forces. All 3 astronauts survived. NASA Review Board traced the accident to a chain involving design change, hardware history, test decisions, extreme heating, and damaged insulation. The mission succeeded because crews and controllers adapted, but the sharper lesson is preventive. A small undocumented mismatch can wait silently until an ordinary command turns it into catastrophe.